for Advent of Code, day 17 we were working on. So the part 2, the problem was basically you've got a bunch of rocks falling down that look kind of like Tetris shapes, but aren't Tetris shapes. And the first half we had to basically drop 2,000 rocks and then say the height of it. For the second half we needed to drop like a billion or billion, a big number. Like that's a billion, so it's like 1,000 billion. I know it's a number that's too big. So I did like a naive approach that basically just ran it again, and it was printing out as it went along. But I've also thought the way things fall, in fact, like we can kind of look at some of this example input. Basically, each time we drop something, we increase the height of this thing by either 0, 1, 2, 3, or 4. Like if this guy dropped right there, it would drop by 4. If it dropped like here, it would only raise it by 2. If it dropped it down here, then it would not raise it by anything, so it would raise it by 0. So we kind of have that range of stuff, and also because these rocks, so each time we pick one rock, but it loops back around on itself, and the same with these winds, that it loops back around on itself. Now, because we might like pick up a rock halfway through this jet sequence, it gets a bit tricky as to where a cycle might go. Now, to test this hypothesis, you can ignore those prints, I guess. But to get that, I printed out some stuff. In fact, if we don't do that grep, we should just get the part 1 answer, which should be right, I think. We can potentially check that. 3068. Right, so we're looking at the example input. But yeah, you'll see when I had this grep as well, it was searching for a particular value. I was just looking myself. So it starts here and it increases by 1, then it increases by 3, then 2, so on. And these are just spitting out the amount it increases by. And we do that by basically storing the last size, and every time we get a new height, we update that last size. So I want to expand on this because, as you can see from this grep, really that whole value is looping again and again, and we can see here we got 1, 2, 3, 0, 1, and then 1, 3, 2, 2, 0, which is same there, and then 0, 2, 3, 4, 0, 0, 2, 3, 4, 0, and 1, 2, 1, 2, 0, 1, 2, 1, 2, 0, and 0, 1, 2, 1, 2, 0. Oh, no, that 0 was over there. So 1, 2, 1, 2, 0, 1, 2, 1, 2, 0, and then this 1, 3, 2, 0, 0 is down there, 1, 3, 2, 0, 0. So this is a loop. Now, I've found this manually, and the loop doesn't start at 0, which is important because we need to kind of find where the loop starts, so it starts there. It doesn't really matter if we work out exactly where it starts. Like we could decide that it starts there and the loop goes to like that point there. It's kind of arbitrary. But we need to be able to basically find the loop and how long it is. So in this, I have worked out that it is 35 long, and it starts after the 15th, which we can see here. We've got 5, 10, 15, and then we have our loop. What I want to do is work on a, so if we go to wikipedia.org, in see if this loads. I recall sometimes Ladybird didn't like it doing that. And then cycle detection. So there's a couple of algorithms that we can use. There's like the Brent algorithm, which is the better one, which is probably what I'm going to use. And there's also one that's like commonly called the tortoise and the hare, which I can't recall exactly what it is. But in here we should have Floyd's algorithm. So Floyd's algorithm has like a tortoise and the hare approach, and we've got some Pythonic code, and Brent's algorithm is slightly better, but both of these, the complexity is order one storage space, and then the cycle size plus the offset size. So this will be like 35 plus 15, and that's the order. And those numbers change depending on what it is. Like, I think if we maybe copy our inputs from day 17.input to input, and then maybe run build day 17, and we just run that, we'll have a different answer. And here we'll have like a different loop somewhere. I don't know where it will be at this point in time, but say if we see if it's the same as the other one, this is where it would go to, and it will go to like there, and it doesn't look like it is looping at the same place. So we would be changing it based on, we would basically be working it out. So what I think we need to do is kind of store these kind of diffs like that, and maybe this can just be a thing of usize, because we will be having usize, and we can have that same sort of thing, and we can go diff stop push and push that last thing, and at this point we should have diffs equals that thing, and if we print that out it will do something slightly different. We could probably still have that grep, and I just realized I want to make a thing 16 by 4 and put it down there, just so I know there's a camera there. Right, so I would have it'll be in a slightly different format when we print it. Day 17. So if we run that, yeah, it's got like a space in between. So maybe if I had like that, then that grep would find it. Yeah, that grep now finds it. But we're not going to be printing out in this format. I just want to see that it's storing it somewhere, and what we will do then is basically go through and do not the Floyd one, I think we'll do the Brent one. So one thing with the Floyd one is both of these have kind of they call it like pointer algorithms. They basically got two pointers into the array, not that one. So you basically have 2 pointers here. So that's going to be, say if you're doing the Floyd one, in fact we could, no, we'll keep it there. We have two pointers, one we call the tortoise and one we call the hare, and to start with, the tortoise will be there and the hare will be like just one next to it. Then each iteration in the Floyd one, the tortoise moves 1 but the hare moves 2 because the hare moves quicker than the tortoise. It's based off Aesop's, I think it mentions it up here. Yeah, Aesop's fable, the tortoise and the hare. Once it does that, it still doesn't really have all the information, and yeah, to do that we need to find, it'll get to a point where it can work out where the start is, and then from the start it can then work out how far it is. So mu is the start of the cycle. That question mark is lambda, and that question mark is mu. You'll just have to take my word for it. Whereas in Brent's algorithm, it's kind of done in one step, so we don't actually have to work out what the length is. So lambda is the length, and it gets incremented in this. So here we know what the lambda is, and we just need to find the mu, and we can do that by doing some other stuff. So yeah, what I think I will do is we will make a function, and we'll maybe just call it Brent, and we will take in maybe a non, maybe we'll see what these call it. They don't really, so they use like different thing where you're passing in a function, whereas we've just got an array of stuff. So we'll just call it maybe a, I reckon a is probably alright, and we will kind of just start at 0, and what we're going to return is maybe a tuple, and we will return that, these two offsets basically, u size and u size, and after part 1 we can probably go how do they return it? Maybe a lamb and mu. I'll just call it the same. We need to like wrap that around like that, and then put Brent on that and on our diffs. And here we can probably go print line diffs equals that, and print line maybe lamb equals that, mu equals that, and then diffs, just so it will show up on that same line when I grep it. Right, so that is that, and for now we can just return zeros and just see whether that still works. And it probably should, yeah, 0, 0. So here we want to basically implement this, and what I might do is, so wiki's like public domain, I guess you'd call it, so like I believe I can just take this and write it myself. So what we have a root power. This can be, now the power is used, we'll just call it yeah, we'll make it unsigned, and we're also going to have a tortoise, and this is going to be the 0th element, and we're also going to have the hare, which is going to be the 1st element. Really it's going to be tortoise plus 1, I guess, and then we want to do while a of, and I think I want to just have t and h, and maybe p, and maybe l, and here we can just return l and mu. We don't actually have a mu equals 0 uz, that's done down there. So we want to do a loop while A and H, our tortoise in here, are different inside of that array. And when that is the case, we want to do this case here. So if the powers are the same, get a new power. So Brent's algorithm does like powers of 2, whereas Floyd's just kind of adds by 2. So yeah, there's mathematical reasons why it is different. So here we want T to just become H, and we want to power times 2, and on lambda we have that, and I wonder if we need that there. And here we just need to have here plus equal 1, and lamb plus equal 1 as well. Right, so now we've done that kind of while loop, and so now we're in this second section here. So T equals gosh, I'm playing with my keyboard, 0uz, and H is also going to be just the same as tortoise. And I think we don't need that, and I think we don't need that because they are sizes and it'll just know what to do. And here, this, I think we can kind of just go here equals, yeah, I think we can just go like that rather than just do a loop, because our f function is basically incrementing the index. And the distance between here and the tortoise is now lambda, so that seems correct. So now we're at this mu point, and we want another loop to test whether our array entries are different, and if they are, we want well, if they aren't, then we want a t plus equal 1. I wonder if we can just go t plus plus, because I just realized I'm reading Python code, and Python for some reason you can't do plus plus, even though every other language in the world you can. And I prefer it, to be honest. And H also just needs a plus plus, and mu also just needs a plus plus. And then we just return it, and I wonder whether this will do the trick. So we'll print out some stuff. We can probably not have that always on top anymore. And so here it reckons 2 and 2. So that doesn't seem right to me, because it's suggesting that this, we're here and our length is 2, so it's finding like length of 2. Yeah, that doesn't quite do what I would want. Yeah, he's hoping for stuff that just magically works. The other option is I could write up this Floyd just to see how that goes. Could be kind of interesting. The function Floyd, and we're going to take in a similar thing, and we're going to return a similar structure. And here, maybe we can make this always on top again. So here we will have mute t equals 0 and mute h equals t plus 1. And while a t is not equal to a h, we do a loop, and t will be plus plus, yeah, this power thing is, so the first one, and then it sets it to that. Do we do that? Yeah, we set the tortoise to that. It'll be interesting why that didn't work. Potentially did, but I'm using it wrong. Who knows? But yeah, now we need to find our rest of the things, and so t plus equals just plus plus, and now we move it at the same speed, and we do that, and then mute L equal 1 EZ, and H can be T plus 1, and while a T not equal to A of H, then we H plus plus, and we also L plus plus, and we are returning L and M. Yeah, and here maybe I'll just do that, except use Floyd. If I can Floyd, and if we run that again, maybe take off this always on top. We can see, alright, so that also just gets 2 and 2, which, yeah, I'm not a big fan of that. I wonder if we do a cheeky start at like 5. Yeah, and where else do we do? That one there. Yeah, maybe if we force it to start after a bit, like the algorithm's meant to do that. Right, so now it reckons the length is 1. So I think what I want to do is like, I don't know, like it's just, this was my grand plan. It was just going to work. Maybe we will do some debugging if we get that back there. Right, so we'll do the Brent. Tortoise equals x equals that. Maybe ti equals that, hi equals that, and a t equals that, and a h equals that, and we can just give t, h, a, t, and a h, and maybe we'll just see what that prints out. Maybe we won't do that great, and maybe we will also just make the output a bit smaller, so we'll just get abort, and maybe instead of the abort I'll just do a return, just so we don't get that pop-up that happens. We can't do that, right, because we need to like return a thing. I mean, return 1 might have been better, but Right, so then it kind of just shows us that. So here, maybe I also want to print. We could do a equals this, but we can just do like a slice. Maybe we should check how to do the slices. Source jakt and get grep slice and samples. Then samples array and slice. So how do we do a slice? Yep, just that 2 to 4. So here we can go 0 to, I don't know, 20. And we can just print what A looks like. So if we do this, right, so we are, in which algorithm? We're in the Brent, so we should get down to the Brent so we know what things look like. Right, so in this, we've actually done a print here. So our tortoise is 0, 1, 2, 3. We're looking at that, and our hair is there. And so we've seen 1 twice, which I guess makes sense. But we want to make sure that like they're all yeah. Yeah. Maybe we will also just have a quick squiz at what P equals and what L equals. P and L. So P is 4 and L is 2. So 3 and 5 doesn't seem right to me. And we never use that power again, but I suppose that power is like resetting it. So maybe we will do a hoping this would just work out of the box, but no. Right, so we do it once when we've moved the hair once. Well, no, we've just moved it. This happens the very first time because power equals lamb there. So the very first time we should So the very first time we should have this situation, they should be different, we don't really care about it, but then P will become 2, well, 1 squared, and L will just become 0 again. But then we'll add to it. Now, do we do that? Yep, we do set L to be 0 and then add to it. Maybe in this loop we can do that in loop and see what that does every time. Because yeah, I was hoping it would just work. Right, so this next time the power goes up to 2 and lamb goes to 1, which looks about right, and our hair has moved and our tortoise has just become whatever the hair was. That looks good, and here they're different still, and P is not the same as L. So the tortoise stays the same, then the hair moves again, so they're all different, at which point they're the same again, so P will become 4 and L will become 0, but then secretly 1, because we add to it, and so the hair, yeah, the hair should move, but the tortoise should just become the hair. Yeah, the tortoise should become whatever the hair was, so it's 3, but the hair goes up by 1. That looks all good. And then in that loop, we increment our hair by 1 again, and our lamb by 1, so we get lambda of 2, and then we see that they are the same, but that is just 1 that's the same. Yeah, that is literally only finding 2 numbers that are the same, not like a whole cycle. So we just believe that it is 2 because we saw 2 2s. I suppose that is legit, because 2 1 2 1, but it doesn't continue looping. So I guess what we should potentially do is have another hair, I guess. Yeah, which we could probably do by AT not equal to AH plus lambda, because we know lambda is going to be the length of whatever cycle, so if we add lambda to it. So say in here we know we've got a cycle of length 2, so we can say look at this, compare it with that, but also compare it to that, at which point that should then fail, I believe. And maybe we can also do a test here, a t not equal to a h plus l, yeah, something like that. And let's see what this does. Right, so now it does a bit better. Maybe, I don't know. What does it return us? Do we not print it out? Oh, we're doing that. Maybe this can be 0 dot dot. What did we do up here? Like 20? Yeah, 20. Just to see what it kind of looked like. Right, so it still reckons length 1 and 2. We're running the brand, and that's what we just changed to have this. I think that needs to be an OR, and this also needs to be an OR. Yeah, so now lam is 7 and mu is 7. So that means starting from the 7th element, so 0, 1, 2, 3, 4, 5, 6, 7. We have a loop of 7, so from there 1, 2, 3, 4, 5, 6, 7 doesn't really look like a loop to me. And what did it reckon things look like? It reckoned they were a 2. Maybe we will also do, at which point, yeah, this L was 7. So maybe we can also do a H plus L equals that, and just before we do the P, we can do a H plus L. Because I feel like that should, it reckons it's right. So there'll be 21. Do we want to add 1 to it? No, I don't think we do. And so 21 will be, right, 0, 1, 2, 3, 4, 5, 6, 7. So we have a 3, 7. Yeah, it's not really right. I'm just unsure how this is meant to detect a like repeating cycle. Maybe we could do something like that. It seems like real hacky there. So I'm just checking whether the next value up is different. This is looking a bit better. Length of 10, but starting with 0. So that means that it reckons we have 5, another 5. Yeah, so now it's just saying 1 and 3. And so it's like must be legit, but it's never really checking the in between. So I think, yeah, this, and this is like right up there on cycle detection, finding a cycle in like a set of values. Hmm. I'm wondering whether I'm using it right. Um, yeah, right. Like, I like this kind of approach, but it needs to rule out stuff that isn't actually loops, because currently it's not doing that. Oh, I shouldn't touch that. I've got a little train toy in front of me. Shouldn't play with things. Wow, microphone's right there. Right. I kind of want to maybe have a function is cycle. This is starting to feel real hacky, but what we're going to pass into it is like our IDX. I'm just going to make these on ID. Actually, no, I probably shouldn't. IDX. And it's going to be a U size, so it's going to be a starting thing. L is going to be a U size. What was H used for? That was to tortoise in the hair. And here we're going to just return a bool. So in this function, what we can do is return true at the end, and in this loop we're going to for I in 0 to L, and we're going to do a thing. And if we see that a IDX so if that is the case, then we want to return false. And in here, I guess, not is cycle and IDX can be T, and I'm going to make it a bit more something like that, and maybe we'll just have one on for that. And maybe see what that does. Or if it's not, I want this. Right, so it doesn't like that. That's because L doesn't exist anymore. Length and length. So this is a bit more taxing, I guess, but it should. Oh, I got a segmentation violation. That's not something I want. Will it tell me what it was? Doesn't really. Maybe we can do a guard here, IDX plus length plus I is less than A dot length, A dot size, only string is that, else we can return false. Maybe that is a good guard there. Basically check that this is legit, and this should be legit because it's a U size, so we don't need to check whether it's negative because it can't be negative. Right, still didn't like something there, so where is it failing? Oh, it does actually print that stuff. Yeah, so I think this yeah, maybe they'll do the trick. Didn't quite do what I wanted. Yeah, because it reckons the length is size 1. But starting from like 7 and 8. So 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7. Yeah, so it's found these 2 2s in a row. So I think this is cycle. Might need to maybe do like 3 times. And maybe we can just loop through all of this and maybe do that, and maybe do that, and 2 times, thank you. Maybe that's that one, and this can be 3 times. I mean, this also kind of feels hacky, but I just kind of want it to be confident that it's repeating long term. This looks better. 35. And I'm like, what did I even say down here? Cycle is length 35, but it was saying it was starting after 15. So I think the problem here is it's not doing that check in this. So we also need to do or not is cycle here with AIDX is T and length can be L, and then we can find a more appropriate mu. Yeah, mu of 15. So that's what I had for that. So yeah, maybe we can get rid of these, and maybe we can just get rid of our Floyd, and like maybe we will also just do that. Maybe we won't, but it will be obvious what that is there. And in here we can probably call this length and IDX, I guess. So how that means what we're going to do. Say we want to find yeah, so we kind of have our repeating thing starting from IDX and we go for length, and we've already done 2022, so I guess we need to work out how far into a cycle we are, and maybe like offset the IDX up by that. So yeah, we've already gone 2022. So maybe mu, maybe, yeah, we kind of want to get 2022. We want to minus off IDX of it, then divide by length, except maybe we want to mod by length. And they'll tell us, it'll shift off that first bit, and then it will tell us how far through it is. So maybe we will do that. Offset equals that, and we can just print that out, I guess. And really what we know that the last size is, we know what the last size is, so we can, from that offset, yeah, we can work out what the next so many values is going to be. In fact, like, it would be good to even like pre-sum it up, or like we could, in fact, I think I want to copy that and put in just to see what that reckons. Right, I didn't like that. Length and IDX, sure. See if these values are different. Right, so is that because it's just real bad, or I don't know. Yeah, it's not a great sign that it doesn't do it. Right, so offset is like 2007 into, no, that doesn't quite make sense. I think we want that and that. And it's not a great sign that it's not doing it for the actual input. Right, so now it reckons the offset is like 12 into this loop of 35. That seems good. But yeah, I want to get that again. And maybe have some prints so we know where that sig fault is happening. It's doing it in here somewhere. So maybe if we go print here, do we get to that point? Do we get there? We don't. So that means that we probably yeah, we also do the I there. Yeah. Print line here t equals that and h equals that t and h. Try and get a bit of info out of what is happening. Yeah, so it looks like h is going out of bounds. Because yeah, we're yeah, I wonder if the cycle is just so much more. So what we could do is just make a bigger cycle. Well, bigger array. Yeah, and that found it. So our cycle length was like 17,000, but we started at 229, so we actually had to go a bit further than 2022. So where I want to go from here, I know the offset, and I know I've been, well, actually no, I've actually been in at that point. And what the, I can't remember what the offset was for the other one. What I'll do is get rid of that one, and we can print that again, and we can also print it with the example input. It's a different value, 1046. No, it wasn't. Because theoretically, that should be the same, but then if we do that and just do 2022 here, we should get the same offset. I believe we got a different one. Does that kind of match what I think? I think that kind of does. Yeah, so we know that that is we've done that many iterations. So we kind of want to work out how much more to get to that point. So I guess at this point, maybe we can have this is a variable, and as we kind of go up, so we want to do this big one. But here, instead of doing s.simulate like we do below, we kind of just want to get maybe we can do last size plus equal to diffs of d plus idx, and then d equals d plus 1. Then mod length, maybe we'll do a space there, and maybe here we can print line part2 can be just last size, and we'll see if that like runs quickly, I guess, and it should give us a answer of a large answer, I guess. Yeah, so now it's got the diff, so now it is spinning up and doing a bunch of stuff. And I guess what I also want to do is have like this, I guess, and maybe this can be and after that then it will be and it will just be the last size. Just so we get some sort of output. So it's doing stuff. So we need to get very big. I think it's printing quite quick. So what I might do is just put another 0 there, just so it's not going too quick. In fact, like even another 0 might be worthwhile. Yeah, like that's still real quick. Maybe one more. And like, how many is that? That's 6, and we're wanting like a lot more. Gosh, we've got a small lockup. It's going real quick, so maybe we will just add in another 3, so 3, 3, 3, and 3, 3, 3. So, oh, I've tried 1,000 times, I guess. And it seems to be getting kind of big enough. I have just not been saving that every time I've been trying to make it print less. That's why no changes happened. That's why it was real quick. I feel like it still didn't do what I wanted. Yeah, because it's only looking at those 4. We've only been changing it there. Maybe that much. So I guess we can probably actually just get rid of this because that will be getting rid of. Yeah, that's good. Maybe goes. It might be too slow. So we find out our thing, then we just start going, oh, that might be a bit too slow. Yeah. Still kind of seems like it will be quite a lot. What I can do though is actually work out that cycle and then just multiply rather than like basically work out how many cycles there are and the increase after a whole cycle, and then just add on those, well, even just multiply the number of cycles we need times that amount, and then just for the last little bit we'll do that offset type thing to get the last little bit. But yeah, this video has gone on a bit, so I'm wondering whether to stop it, because this is, yeah, it's still just going to take, that's 9 there, and that will be 9. So it's still going to be, once this gets to one more digit, it's still going to have 1,000 times more of that, which seems too slow, just too slow. So I think mute cycle size equals 0, and maybe we'll call it UZ. And here we can, for I in, we start at IDX and we can go to IDX plus length, and we can go cycle size plus equal to diffs of I. Yeah, that'll do the trick. And here we want to like do that many more things. Let rounds. In fact, I kind of want to reach rounds equals 0, and then rounds plus plus, and maybe like while rounds is less than 10, do that, and we can just go rounds plus plus, and here rounds to go can be this whole thing, minus rounds, which should be 10,000, and then here we want to get rounds to go and mod it by length. No, we want to divide it by length, because that tells us how many more cycles we want. But we also want rounds to go mod by length, to, I guess each of these we need a minus IDX, and do that. And so this amount here is going to be the number of cycle sizes, and we can probably just add that to last size plus equal to that, and maybe I will get rid of that and just see if that kind of prints a feasible answer. Right, it doesn't like things. Cycle size might be not the right type. Cycle size. It should be good. maybe we can do UZ just for the rounds. Yep, that did the trick. Vroom vroom. Alright, so here, yeah, it gave an answer, and like it looks in the right realm of things. So now we just need to like add on what is left, I guess. So that's going to be that, and then for I in IDX to IDX plus IDX plus cycle left, do that sort of thing, and then maybe we can go to last size plus equal to diffs I, maybe something like that. And I think because I feel close to the final solution. Oh gosh, is that it? No. I think I kind of want to start with a smaller number. So we know what 2022 is meant to be. So what I could do is we could potentially like do a temporary thing. Maybe we'll do this. We can just create a new simulator. We can create a bunch of things, but we will only go to like 35 maybe. Maybe we'll go to 40. And maybe we'll go rounds equal 0. And maybe not do that. So here we're going to have all of this code, I guess, but maybe with like that sort of thing. And here I want to go 22, I like that. And theoretically we should get the same answer as part 1. So we can see what that looks like. And if that doesn't work, maybe breaking it down into a much smaller thing of, say, what's 36? It's like super close, but it needs a couple more added on, or like a different amount. So I guess if we say if we wanted to get, say, just 41, let's just draft this up. We want to get 41. We've had 40 so far. Loop starts at 35, so we want to basically offset. So this doesn't quite seem right. this case. So 1 minus 35, that will just underflow. So I think we don't want the minus IDX there, because we've got one thing to go, and here we probably don't want it there as well. So 1 mod the length of 35. So 1 divided by 35 should be 0, then 1 mod 35 should be 1. So it means we just need one more. And I think we want to add IDX there. Wow. We want to know like whereabouts it is offset by. Because yeah, we're gonna have like the end. So say if we want to, instead of 41, we want to go 71. Where did it start? It started at 15. So say we want to do 85, and we've done 40. Maybe we want to do 86 just for shit and giggles. We've done 40. We start at 15, so IDX is 15, cycle equals 35. Length is what we call it. Length equals 35. So to go equals 86 minus 40 equals 46, I guess. So there's 46 more things that we need to do, but we need to know that we're 5 through. So I guess there's 40. We need to. If we get rounds minus IDX, because we need to know that we've already gone through so much. Not a fan of these like fiddly math things, especially on large-ish things. Like we've got a length of 35. Potentially we could do on a smaller amount. So say we have 1, 1, then 2, 3, 4, 2, 3, 4, 2, 3, 4, whatever. So here we have, and what's that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we'd have rounds equals 11. We'd have IDX equal to 2, because that's where we start the cycle length. We would have length to be 3, I guess. And say we want to find 15. Find 15. So the cycle size, we get that from somewhere, don't we? Yeah, cycle size we do get. So cycle size equals 2 plus, there's my plus, 3 plus 4 equals 9. Right, so rounds to go. So this is going to be 15 minus 11 equals 4. and we need to, I'm going to do that. Just because I want to end halfway through a cycle, because there should be a 4, then 2, 3, 4 example. So 15, and so we will expect plus 2, 3, 4 is 9, plus 6, so 15. So we're going to expect plus 15, so rounds to go. We are going to get that to go, and we're going to divide it by our length. So that's going to be 1, it's like 1.6, but we'll get truncated to 1, and we'll times that by the cycle size, which is 9, so we'll add 9, add plus 9. Now we need to, so we basically added this bit, but now we need to work out that we need to add that and that. So from there we need to work out the outside. So if we take rounds and we minus off IDX, so minus 2, so that's going to be 8, which should be the start of a which happens to be a start of a thing, doesn't mean it has to be, because like say if it was like that, then we'd subtract 3 off, but yeah, alright. But yeah, that 8 we can then divide by our length, and that's going to give us 2. Maybe we want to mod by that, so that will give us 2 with 2 remaining. So that means we've done 2 of the thing already done. So that means we could, from that index of this thing, so it'll be IDX plus 2, so it'll be there. That looks good, and it'll add us that 4. And then we also will get the 15, and maybe we'll do a similar thing and get that. So 13, there'll be like 4 with 1 remaining, which makes sense because we're only 1 over, and if we were smack bang on it, it would be 0, so we want to get 1 of that more to go. So how would that look? That would look like for I in, this is going to be let's end start IDX equal to, this will be rounds minus IDX mod by length. And we need like an end IDX for that. Because we need to know that we're only going to go up to 3, though that will be, yeah. So for I in just want to go to length, and it should be less than length. Yeah, that sounds good. And here we can just add to last size, and we'll go diffs idx plus I. Yeah. And in idx, this can be our expect. What expect isn't what I want. We want search, I guess, and that can be one this many. And we can call this search minus idx mod length for I in, and this will be just one more to go from the idx. So this will be 0 in 0 to end idx, and here we will go last size plus equal diffs idx plus I, and they'll do the same thing just for the tail half. And we also want yeah, I didn't show my working there, but I had it before. It was something like 5 mod 3 equals 5 divided by 3 equals 1, and then add times 9 equals add 9. Right, so that is it's this kind of thing here. Rounds to go. Yeah. So this can be search rounds so far. Last size is going to be that minus that times that, and this thing can get changed into these things. Yeah, maybe that will do the trick. And maybe we'll just try and run that. We could also yeah, I was thinking we could do all of this, I guess, after this, except we set that to be 022 UZ, and maybe we'll just do that whole thing. Last size is alright. We do need that, and we do need that, and we probably need that there. And the rest is like pretty good. And that print will be the same. Is that the right answer for that? It looks like it might be 15142, 15142, 857, 14288. And if we run it again, and maybe remove some more print stuff here, we can do that. And what I'm expecting is part 1 not to be that big. That will be because of that. Right, so now I would expect part 1 to be 3068, both the first and the second time it prints it. The first time it is, because that's good. Then it should print the yeah, cool, so that's perfect. So that means we can probably get rid of all of that and print the day 2. And so now if we copy that, and it's running like pretty quick, I'm liking that. So if we run the actual input, it should be quick-ish. Had to think, but it got this output. Gosh, I was can't paste. Yeah, even for the Control V now. 159, 197, 707, 735, 2, and can't even see the edge of it, but that's alright. I reckon it's the right one. Yep, that is. But we can copy this and go not IP outputs day 17 output and do that one and get rid of that. And if we run test for 17, it should pass. Though it might fail on the example input because we don't put that massive number there, which I'm gonna assume just exists. Oh gosh, it's that is right. Then this one, I can't do that. I forgot. Example and part 2 can be that number there. And now if we maybe run a reset and do that test, it should pass for both. I'll do that back arrow. And some of you may have noticed I actually have 2 stars for day 16 now. So I used one of my friend's programs for day 16 to see if it worked, and his solution got me a solution, which is kind of annoying. I couldn't check whether it was the right solution without putting it in the system, and then it told me it was the right one, but then I can't like undo it, and so my actual code does not, well in fact it doesn't even compile in Serenity, which I've talked about in the past, but yeah. I will potentially come back to day 16 at another time, but for now day 17 part 2 is done, and so we can push that up, and I think that is a good time to say thanks for watching for the video, and hope you enjoyed, and I'll see you next time for day 18 or maybe day 16 part 2.